Hello. In today's experiment, we will use Ohm's law to measure the resistance of a conductor, and we will determine the resistivity of the material of that conductor. Well, to begin with, I don't know whether you have covered this in theory yet, but how would you allow a current to flow in a conductor? A current flows in a conductor when there is a potential difference across its ends. Well, so I have now used three terms: potential difference, current, resistance. Now, potential difference we will represent by the letter V, current by the letter I, and resistance by the letter R. Potential difference is measured in volts, and volt is V. Current I is measured in a unit called ampere, and we will use it uppercase A for ampere. And resistance R is measured in a unit called ohm, the name of the person who studied this, and the symbol for ohm is the uppercase omega. Well, what does Ohm's law say? Ohm's law says that you apply a potential difference across the ends of a conductor, a current will flow in it, and greater the potential difference, greater will be the current. You increase the potential difference, the current also will increase. In other words, potential difference across the ends of a conductor is directly proportional to the current that flows in it. That is Ohm's law. And replacing the proportionality sign by an equal sign, we get V equal to Ri. Well, this is the equation we are going to work with in today's lab. We will take a conductor that has a given resistance. Well, that is a constant for a given conductor. We will apply different values of potential difference and measure the corresponding values of I. Is that right? And this equation is of the form y equal to mx. So if you now draw a graph of V volts on the vertical axis and I ampere on the horizontal axis, you will get a straight line, and the slope of that graph will be equal to R. Now, you will measure the resistance of 5 different conductors. Now, let me show you the kind of conductors you will be using. Now, I explained using this conductor. This is an aluminum rod, a good conductor. But the conductor you are using is a long wire which is wound on a frame like this. Well, there you are. And the length of this is 120 centimeter. Well, I have different lengths. I have let me show you the ones you will be using now. I have another one which is 80 centimeter. Well, the camera has difficulty focusing onto it. Well, that's another conductor. Another one, you have 200 centimeter. There you are. And like this, we're going to use 5 different conductors, but all of them of the same materials. All right, so we are going to use 5 different conductors, all of them of the same material. And because their lengths are different, their resistance will be different. So you will measure the resistance of each of these conductors. That means you will have 5 different graphs. Each time we will measure the potential difference and current and draw a graph of V against I and measure the slope. So you will have 5 different graphs, and that will measure the resistance of each of these conductors. Alright, I will show you in a minute how that can be done. Now before I go to that, let's talk about this resistance. What are the factors on which the resistance of a conductor depend on? Well, let me take this off and let's write down some of the factors that affect the resistance of a conductor. If I increase the length, will it increase or decrease the resistance? Well, increasing the length will increase the resistance. So I can say resistance of a conductor will be directly proportional to its length. How about the thickness of the wire? What do you think? If you increase the thickness, will the resistance increase or decrease? Remember, resistance is the resistance offered by this conductor for the flow of electric charges through it. You know that if you have a corridor which is very wide, the resistance for the flow of people through it will be less. Is that right? You can move much more easily. A crowd of people can move much more easily in a wider corridor than in a narrow one. So it means you increase the area of cross-section, the resistance will be less. How do I write that? Resistance is inversely proportional to the area of cross-section. I can combine the two together and write it like this. R is directly proportional to L over A. And now, for all the conductors that we will be using, the cross-section is a circle. That means the area of cross-section will be the area of a circle, which is pi r squared. And I'm going to replace the proportionality by an equal sign, and watch this equation. R equal to rho times L over A, where this rho is a constant for a given material. In other words, the rho doesn't depend on the length or the area. It is a constant for a given material. And this rho is called the resistivity of the material. The resistivity of the material. And we will be measuring the resistivity of the material of these 5 conductors. Actually, the material of these conductors are nichrome. It's made of nichrome. And we will be measuring the resistivity of that material. Alright, in order to do that, let's rewrite this equation. But before that, what is the unit of resistivity? If you want to solve for it, you can say rho equal to RA over L. Well, resistance is measured in ohm, area is measured in meter squared, and length is measured in meter. Therefore, resistivity is measured in ohm meter. That is the unit of resistivity. Remember, when you write your report, every physical quantity must have its proper units. You lose points every time you ignore to write a unit. Alright, let's now start with this equation. This is the working equation for our lab. R equal to rho L over A. And now, I told you we will be working with 5 conductors. Now, all of these 5 conductors have the same radius. They are all of the same thickness. That means the area of cross-section is a constant. In the lab manual, I have given you the value of the radius. You can calculate the area of cross-section. And rho is a constant. Therefore, this equation can be written as R equal to rho divided by A times L. So, you have measured the resistance of these 5 conductors, is that right? And if you make a table, what are the resistance values? And I will give you the lengths of each of these. Each time I use a conductor, I will give you the length and you need to make a note of that. Length I'm going to give you in centimeters, but you need to have them in meters. Alright? Now, you need sample 1, sample 2, sample 3, sample 4, and sample 5. You have the resistances that you have measured in the first part of the experiment, and each conductor has a length. You will draw a graph of, what kind of graph you will draw? Resistance on the y-axis and length on the x-axis. The slope of this graph will be rho divided by A. And you know A because A equal to pi r squared. I have given you the value of R, therefore you know A. And so use the slope you obtain from the graph for calculating the value of rho, the resistivity of the material nichrome. Okay. And now let's see how we can set up the experiment for the first part. What is the first part? Measure the resistance of 5 samples of nichrome wire. And that is our first part of the experiment. Now, this is the Ohm's law equation that we will be using to work with in this part. V equal to Ri. That means we need to measure the potential difference across a conductor and the current I that flows in it. Alright, let's first of all set up the circuit. A conductor in an electrical circuit is represented by this symbol. This is a conductor. And we will connect this conductor to a cell or a battery. Now, here I have a battery. We will connect the conductor. Now, that is our conductor, which has a length, is a wire which is wound to a frame. If you open it up, it will be a long conductor. Alright, connect the conductor to a battery. And from the other end of the conductor, I'm going to use what is called a variable resistor. A variable resistor is also known as a rheostat. The idea of the rheostat is by varying this, we can vary the voltage, the potential difference, so that we can measure the current I for different values of V. That's a rheostat. And then you connect an ammeter to measure current, and that is the complete series circuit. You see, the conductor, this is the conductor we are going to use. That is the conductor. This is the battery. Alright. This is the ammeter. This is the rheostat. That is the series circuit. And now, so the ammeter will measure the current I, and you need to now measure the potential difference between the ends of the conductor. How do you do that? Connect a voltmeter right across the conductor. That's the way we connect the voltmeter. So the voltmeter is connected in parallel to the conductor, and the ammeter is connected in series with it. Alright, now let me show you how that can be set up with the equipment that we have. Before I set up the circuit for you, make a note of these. The 5 conductors that we will be using will have these lengths. So when I say sample 1 or conductor 1, this is the one I'm using. That is conductor 2, that is conductor 3, conductor 4 and conductor 5. Alright, take a note of that. Let's now take a look at the equipment that we will be using in this lab. We have the conductor which is hiding behind here. This is your conductor. This is the coil of wire I have connected to alligator clips so that I can make easy connections there. Okay, and this is the rheostat, the variable resistance, and you can see when I connect it I will explain to you how it works. Alright, so that's the rheostat, and now this is the battery, this is the ammeter, and this is a digital voltmeter. It will be easy for you to read. Now let's take a look at the connection. I hope you made a diagram of the drawing I made on the board. Now look at the way I'm going to connect it. I have the conductor connected to the cell, and now I make a connection to the conductor. I plug that in and connect it to the cell. There is the cell. There I made the connection to the cell, and you see if I can make these connecting wires behave. And from the cell, from here, where do we go? From the cell we go to the ammeter. So what I'm going to do is I'm going to make this connection over here to the cell, and now from the cell I go to the ammeter. I make a connection there to the ammeter, and there it is. That's the connection to the ammeter, and from the ammeter where do we go? From the ammeter we need to hide these wires to make it easy for you to see. Now from the ammeter you go to the variable resistor, and the variable resistor is this. I will move it from there after I have finished with the connection. Now if you noticed, I'm going to send the current in here. Look at the way the current is going to flow. It's going to flow into here and through this rod, and then it will come into this wire and out over here. There you are. And I'm going to now make a connection from there, and it will come back to the conductor. Is that right? It comes to the ammeter, and it comes back to the conductor that is here. I have now the complete closed circuit that is made. Now look at this one more time. Start from the conductor. This is our conductor whose resistance is to be measured. From the conductor my connection comes to the cell. From the cell it goes to the ammeter. From the ammeter it goes to the rheostat, and the current flows through here. And look at this, I can change the position of this so that the current and the voltage can be altered. And now it will come back to the conductor. We have the series connection complete. Now I need to connect this voltmeter across the conductor. What all I need to do is get 2 more connecting leads and take one end from that conductor and connect it to the voltmeter there, and alright, and another connection from the other end of the conductor, that is here, and goes to the other end of the voltmeter. I have now connected the conductor, the voltmeter across the conductor. The voltmeter will now read the potential difference. Now, if you look on the ammeter, can you see the pointer moving? Well, it is reading the current values, and the voltmeter will then read the potential difference. Now, what you should notice is that the potential difference values that is shown by the voltmeter is actually in millivolt. In the experiment, I will use the rheostat to change the values of the current, and I want you to read the current from the ammeter. I will focus on the 2 meters. Well, it's easy to measure the digital meter, but it will take some experience to read this meter. I will explain this to you. I will change the current values, and you measure the current and the corresponding potential difference. Try to get about 6 different values. 6 values of current and 6 values of potential difference, so that you can draw a graph of V against I. I want you to look at the ammeter and see how the reading is taken. If you can see my pointer, you see that's the 0, and you will be using the lower scale. This is 0.5, so take a note of that. 0, 0.5, 1, 1.5. That's the maximum. Now, don't look at the top readings. You are using the lower readings. So 0, 0.5, 1 ampere, 1.5 ampere. And if you look at this, the 0 and 0.5, in between there are 10 divisions. That means each division is 0.05 ampere. Alright, now you can read the ammeter readings by using that. So this will be 0, 0.05, 0.1, 0.15, 0.2, 0.25, 0.3, 0.35, 0.4, 0.45, 0.5. That's how it goes. Okay, I'm now going to turn on the circuit, adjust the rheostat, and I want you to take the readings shown by the ammeter and the voltmeter, and the voltmeter will be reading in millivolt. In other words, 1,000 of a volt. You need to write them in volt. Okay, there I have turned on, and I'm going to adjust the current, say there. Alright, now look at the shadow of the pointer. That is where you take the reading. Alright, measure the ammeter reading and the voltmeter reading. That's your V and I. This is your current values. That is your potential difference V values. Measure that. I'm going to change the current value. Okay, take the next value now. Alright, that is the second value. Measure that. Look at the shadow of the pointer. That's where you take the reading. All right. Take the next one. Next reading, the third reading. Done. The fourth reading. All right. Take a fifth reading. Now if you notice, the voltage is now has gone in volt. So now it is in volt. The millivolt has now been given way to volt. So that's 1.152 volt. So previously you had to read those in decimals. And finally take a sixth reading. There you are. Okay, you got 6 readings for this sample. I'm now going to change the sample. Okay, now I have the second conductor that is 80 centimeter long, and let's see if we can get some readings for that. Okay, let's get the current values. All right, take that value, take this current and this potential difference. Now remember, you can see now the potential difference is actually now in volt, 0.382. Is that right? Okay, next, the second reading. That's the second reading. Take that one. No, wait a second. Over there, the second reading. Right. The third reading. All right, the fourth reading. And now the fifth reading. All right. Let's see if we can get a sixth reading. We are finished with the reading. Let's go for a sixth reading. All right, there is the sixth reading. Okay. All right. Now we have the third conductor that is 120 centimeter long. And let's connect it up, and let's take the first current and voltage value. Now remember, the voltage now read by this is in decimals in volt. So remember, this is now 0.943 volt. Is that right? Yes. And it tells you here that this is measured in volt. All right. Okay, take the current and potential difference. That's the first value. Let's go to a second value. All right, take the second current and potential difference. And now a third current and potential difference. Okay, Let's get a fourth value of current and potential difference. Try and measure the current as accurately as you can. You can read between the lines. Alright, now a fifth value of current and potential difference. And finally, a sixth value of current and potential difference. Okay, we got 6 values of V and I. You can now draw a graph and obtain the resistance there. I have now connected the fourth conductor, and let's measure the current and potential difference values there. Start with a low value. Alright, let's start there. Measure this current and potential difference values. Okay. Let's now measure a second current and potential difference values. There we go. Take the second value of current and potential difference. And now a third value of current and potential difference. A fourth value of current and potential difference. And finally, a fifth value of current and potential difference. Okay. I have now the last conductor, that is 200 centimeter long conductor. Let's take the current and potential difference values there. Alright, take that value of current and potential difference. Alright, have you measured? Alright, wait for the study. A second value of current and potential difference. Alright, that's the second value of current and potential difference. A third value of current and potential difference. There we go. Okay. A fourth value of current and potential difference. A fifth value. And finally, a sixth value of current and potential difference. Okay. All right. So for each conductor, you will have a table like this. Trials, the potential difference, the current, and of course the length of the conductor. and then you draw a graph and obtain the resistance. There will be 5 tables and 5 graphs, and now use all those resistance values here. We got 5 conductors and 5 resistance values, and each has a different length. Alright, the graph of R against L, the slope will be rho divided by A. Obtain a value for the resistivity of the material. Alright, if you want any help with the questions at the end of the lab, let me know and I will help you. Alright, I will see you for the next lab later on.